Previously, we looked at the idea that matter can at certain times behave like a wave. In particular, we looked at diffraction of electrons through double slits. We're going to look a little bit more closely at what it means for matter to be a wave and at a particular example of what's called an infinite square well. So all waves tend to have something that's oscillating. Ocean waves have water that's oscillating. Waves on strings have strings, obviously, that are oscillating. Even electromagnetic waves, even though they don't have material that's oscillating, they have an electric field that's oscillating and a magnetic field that's oscillating. So for these matter waves, what is it that's oscillating? It's not that we think that the electron itself, this particle, is whizzing up and down in a wave-like fashion. It's this other thing that we call the wave function, and we don't really know exactly what it is. That's still kind of an open question. It's a matter of philosophical debate in a lot of ways. It's kind of an interesting question because we want to know what our most fundamental theories are telling us about reality. So let's try to relate this wave function idea to a wave that we might be more familiar with. If I've got an electromagnetic wave, a light wave, then the intensity of that light is proportional to the amplitude of the wave squared. We looked at this a little bit when we studied waves. And if I think about that light wave in terms of particles, then I can say, well, the number of photons in a given location is proportional to the amplitude squared. And this is just how the energy works out. But if we think about what this might mean, well, if I have a wave, the amplitude is the displacement from equilibrium. So this is my equilibrium line. The amplitude is this height here. So it turns out we have to square that, and so all of these are going to end up positive, and they're going to end up a little bit taller. They should be uniform, but I'm not great at doing that freehand. So this here is going to be amplitude squared, whereas this here was just amplitude. So this amplitude squared, that's where I'm likely to find a whole bunch of photons, whether it was here or here. If I'm just doing this in one dimension, in x. We don't want to have negative amplitudes because that just kind of doesn't make sense when you're talking about, oh, I'm going to find a lot of electrons in this negative location. So we square everything to make it all positive, and that is where we're going to find the photons most of the time. Did I say electrons? Probably. It works for electrons too. Now if we think about this relationship a little bit more, this tells us where the amplitude is high. That's where we're going to find a large number of photons. But if I have a single photon and I'm sending it through some double slits, let's say, the amplitude tells us where I have a high probability of finding that single photon. So if we go to our kind of double slit picture here, we have this pattern here that hopefully we're somewhat familiar with and have an idea of what we're talking about. If this is light, we're going to see bright fringes. If it's electrons, we're going to see electrons pile up here and here. And again, this is for large numbers of particles, we would see this. But if I'm shooting a single particle, this wave will still tell me where it is more or less likely to hit the detector. It is less likely to hit the detector here and more likely to hit the detector here or here, one of these peaks. So that's what this matter wave thing is telling us, something about the probability of finding our particle in a given location. So we define the matter wave, as I showed in that previous slide, with a psi. So this is known as the wave function. And then when we want to convert this into a probability, we have to square it. And so this is called the probability density. Probability density, sometimes also known as the probability distribution. So that is kind of what this matter wave is talking about. It helps us predict probabilistically where we can find a particle within a given environment. So if we're shooting electrons at double slits, we can use the wave function to describe the waves that are diffracting through the slits, just like we did with light waves. But then we actually have to do the psi squared to get the probabilities of where those waves are going to hit on the screen, or where we're likely to find those particles on the screen. All right, now let's apply this idea to what we call an infinitely deep square well potential. That's a really confusing name, probably means nothing to you, don't worry about that. The idea here is maybe this rigid box idea is a better way to think about it. If you have a particle that is inside of a box that has like impenetrable, really thick walls, so there's no way it could ever get out. This is one way we could model that situation. So we're not saying that there's like a ball that's stuck in this hole, even though we call it a well. We're just saying that you're in some region where we have zero potential energy. This U here is one of the ways that physicists write potential energy. So this is potential energy. So when you're inside this box, you have zero potential energy, and you can move around, you can have kinetic energy, but you can never get through the walls, because this pink area here are the walls, and as soon as you get into the walls, the potential energy shoots up to infinity, and so you would need an infinite amount of energy to have a chance of getting through those walls. In real situations, you could model something like a proton bound in a nucleus with this square well potential. So it's stuck in that nucleus. It can move around a little bit. It can get more energy. You can have excited states for nuclei just like you can for electrons. But it's not likely to ever come out of that. This is not a great way to model that, but as a rough idea, those are the types of things we mean. So they're bound states. You could even model an electron in an atom with this. It won't be a very good model, but that's the basic idea, and this will give us a little bit of a feel for how we apply this wave function idea to different situations. And this is about as simple of situation as we can come up with. So first off, we presume that our wave function is a wave, and we presume that it's a sinusoidal wave, just kind of like we did with waves on a string. And it could be a combination of sines and cosines. So if I say my wave function psi is a function of x, where my x-axis is going this way, so it's going to tell me about the probability of the particle, whether it's a proton, electron, whatever you want, a particle in this box being found at a given location between x equals 0 and x equals L. That's what my wave function is going to inform me about. But I don't know what my wave function looks like yet, so I'm going to have to try to figure that out. Well, it can be a sine wave with some amplitude. I'll just call it some generic amount A. And then I'm going to use this symbol k times x. This k thing here is pretty much like the frequency. Like if we had a wave that varied in time instead of space, we would say frequency times time. But since we're varying in space, we're using x instead of t. And this k thing here is kind of like the spatial frequency. It's defined as 2 pi over the wavelength, and it's sometimes called the wave number. And I'm going to come back to that in a little bit. Now, it might not be a perfect sine wave. It could have a cosine wave mixed in there. So I'm going to use another arbitrary constant for the amplitude of the cosine wave, cosine k times x. Now, you do have to have the same k. You can't have k1 and k2 because otherwise you'll get like beat frequencies and weird combinations going on. So let's take a quick look at sinusoidal waves in Desmos, just to get a feel for what these how these factors affect our waves. So to start with, here I just have a regular sine wave, and here's the equation for it. A, which is just some generic constant. I can change A, that changes how tall the wave is. And then I named it k times x. So if I adjust k, that affects the frequency. Bigger k is like higher frequency, and our wave has more wiggles per unit length. Okay. Now we could also have a cosine wave that's going to vary similarly. I won't bother moving those. But we can think about adding those two waves. And this is just the principle of superposition, where you add the value of the wave at each point. And so here I called it P for psi, because I can't do a psi symbol in Desmos. And here is the sum of those two waves. So I'm going to turn off these other ones so it doesn't get too confusing. Now, as we vary k, obviously that's going to vary the frequency. But depending on the relative amplitudes of these sines and cosine waves, we can get different things going on. We can shift the wave left and right. And so anyway, the basic idea is we can get almost any shape of sinusoidal wave. Sinusoidal is just a sine-like wave. By combining a cosine wave and a sine wave with different amplitudes. So that can kind of change the initial conditions, where the sine wave meets the edge of the box and those types of things. So that's why I'm using that equation, is it's just a nice generic expression that can give me all kinds of waves. Alright, let's go back. Okay, so here is our general expression for any wave, and we're going to try to figure out a specific equation for the waves that will fit nicely in this box, and also waves that will obey conservation of energy. So in general, we can say that the kinetic energy plus the potential energy of any object is equal to the total energy. Now, in this particular situation, we are saying that the potential energy when you're inside the box is 0. If you tried to go out, it would jump to infinity, and you don't have infinite energy, so we're going to be confined inside the box where the potential energy is 0. In that case, we have just kinetic energy is the total energy of the particle. Now, kinetic energy, another way we can write that is the momentum squared over 2 times the mass, p squared over 2m. And just so I could show you real quick, p squared is m squared v squared over 2m. So the m's cancel out and you got 1/2 mv squared. So this is equivalent to kinetic energy, right? And I'm just going to write this as E, since it's the only E left we have now. Okay, now I'm going to jump back over to this K here for a second. We'll come back to this. I can write this K in terms of the momentum as well, because we have the relation, the de Broglie relation for the de Broglie wavelength, where we have lambda equals h over the momentum. So if I plug that in for my wavelength here, I've got 2 pi over h times the momentum. So this gives me a nice relation between k, my wave number, and momentum. I'm going to go ahead and solve this for momentum, and you get kh over 2 pi. And this is essentially where we're introducing our quantum stuff into this situation here. Alright, now if I plug this in over here to my energy expression, I'm going to have k squared h squared over, I'm going to have a 2 squared, which will be 4, and then combine with that 2, so I'll have a big fat 8 there, times pi squared times m, and all of that equals the possible energies that I could have in my box here. I'm going to modify this again later. Alright, so the next thing we're going to do is apply what we call boundary conditions, and this is a really common thing to do in quantum mechanics. So even though this is a simple situation, these same types of strategies are applied to much more complex situations and give us really powerful expressions to explain what's going on the atomic level inside atoms and all kinds of situations. Alright, so I know that my wave function, which tells me something about the probability, or at least the wave function squared does, of finding a single particle at that location, or if I've got a bunch of particles, it tells me where I'm going to find most of them. I know that that has to go to 0 at the wall, because I have 0 probability of the particle going through this wall. So one boundary condition I can apply is that at the location x equals 0, my wave function has to go to 0. And also at the other wall, so at the location x equals L, my wave function also has to go to 0 there. So let's start with this one. If I just go ahead and plug in 0 here, so I'll have psi of 0 equals a sine of 0, almost made it a theta, too used to doing that, b cosine of 0, and this whole thing has to equal 0 because my wave function has to go to 0. Now, sine of 0 is 0, but cosine of 0 is 1. So what this expression says is that b is equal to 0, which is fine. We're just eliminating some of the possibilities for our wave function. We still have a wave, right? We've essentially narrowed down our options to just a pure sine wave as the possible things that can fit inside this box. So some amplitude times sine of kx. Now if we go ahead and plug in this other condition over here, psi of L, just using what we've got left over here, we've got a sine of k times L, there we go, is equal to 0. Now we could say this tells us that a equals 0, but if a equals 0, and b equals 0, then we don't have a wave at all, and that's not interesting. So we could also say that this sign of KL goes to 0 whenever KL is equal to some integer multiple of pi, because that's when sign goes to 0 at pi and 2 pi and whatnot. Okay, so this gives us another expression for k. It's equal to n pi over L. And this is going to be useful. We can take this thing here and we can plug it back into our energy equation here, and we can also plug it in here to our general expression for our wave function. So, wow, sometimes this thing goes crazy on me. So we can say a sine of n pi over L. And this is nice because we're starting to get an expression in terms of the dimensions of this box. I used a capital L instead of a script L, but same idea. And I've got an x in here. Okay, the last step for our wave function is we can actually get an expression for this amplitude. It requires some calculus, so if you don't know calculus, don't worry about it. But essentially, the probability of finding this particle at different locations in the box, all of those probabilities have to add up to 1. You can't have a probability greater than 1 for the sum of all the probabilities of where the particle could be in the box. So we do what we call normalizing the wave function. And so if I add up the probabilities, which is psi squared times dx, adding them all up, man, having problems. If I try to erase it, I'll probably just make it worse. Anyway, we have to do an integral to add up all of those probabilities, and we integrate from 0 to L, and we set this thing equal to 1, and that allows us to solve for the value of a, and a works out to be root 2 over L. If you don't follow that, don't worry about it at all. You can still just use this equation and go on your merry way, as long as my inking stuff doesn't keep screwing up. Okay, so here we have a nice expression for the waves, the matter waves that can fit inside that box, and they will tell us about the location, the probable locations of the particle that's confined to this box. We can also plug this k in over here and get an idea for the energy levels that this particle can have inside the box. So if I go ahead and plug in n pi over L, I'm going to have n squared, pi squared, still an h squared on top. I'm going to do the 8 pi squared here, and then I've got the L squared from that guy. And then m, the pi squareds go away, and all of that is equal to energy. I'll rewrite it. So energy as a function of n is n squared times h squared over 8L squared m. Now for a given box, all of these things are constant except for n. So if we plug in n equals 1, we'll just get this. So I can just call all of that stuff the first energy. And the other energy levels are just going to be multiples of that first energy, where they will go up as n squared. Okay, so you'll need to make sure and write these two things down. You should probably write this down too. That's going to come in handy in a couple of problems that you're going to solve. So this tells us about the energy levels, and you'll notice that these energy levels, the spacing between them increases with n, which is the opposite of what we saw with the Bohr model. So this is not a good model for the electron in a hydrogen atom. This is just a good way to apply quantum mechanics to kind of a made-up situation. But we can apply these same ideas to more complex situations and get some great equations that are very precise. So let's look at our results for our particle in a box a little bit here. These energy levels are going to increase in spacing. And these wave functions, our first one, it's a lot like waves on a string. We just get half of a wavelength. This is kind of our fundamental. We don't call it that anymore. This is called the ground state, or sometimes it's called the 0 point energy. Okay, and then your next one is going to look like this, and so forth. Then we have a little gap here, and we skip up to the 10th. So we're going to have 10 different peaks here on our 10th energy level. And if we square these, it's going to kind of make these taller. It'll make everything positive. What this thing is telling us, this is the probability, remember, a probability distribution. So this is where we're likely to find the particle in a box. So if I have, if we go back to the box analogy, if I have this impenetrable box with a cavity on the inside, and there's a particle stuck in there just bouncing around. The most likely place I'm going to find that particle is right in the middle of the box, if it's in the ground state. If it's in an excited state, I'm not going to find it ever in the middle. I'm most likely to find it here and here. If it's in a third excited state, I could find it in the middle or on the sides of the box and so forth. So that's what this is telling us. Now back to the idea of the Bohr model. If you remember our expression from the Bohr model, the energy levels were negative 13.6 electron volts over n squared. So now we're multiplying by n squared, whereas before we were dividing by n squared. And so that's why those energy levels got closer together instead of spreading out. We can derive, using quantum mechanics and quite a bit more rigorous math, we can derive the wave function for the electron in hydrogen, and it actually works for other atoms as well. We mentioned in the Bohr model that it was kind of a stepping stone to quantum mechanics, and it worked for hydrogen, the energy levels of the electron in hydrogen, but it didn't work for other atoms at all, and it kind of broke some of the rules of quantum mechanics. It doesn't follow the uncertainty principle, so it was kind of a pseudo hybrid between quantum and classical dynamics, and so it was a good stepping stone, but it's not really considered all that useful now, other than for kind of pedagogical reasons, I guess. So here is the full-on nice wave function for the electron in hydrogen. If you're interested, don't write this down. We're not going to use this at all. But it's this big nasty thing, which is a whole bunch of nested things. Like if you look at this thing here, that breaks out into this, and this part here breaks out into that. And so it's this big, ugly, complicated thing. But solving this equation right here is what gives you all of those shapes for those orbitals. If you've had some chemistry and studied the shape of the SPD and F orbitals with the spherical shape and the dumbbell shape and the clover shape and all of that, those come out of quantum mechanics. We didn't like use a microscope and look and see those orbitals. Those orbitals are direct predictions of this equation right here, which is derived from quantum mechanical principles. And I should say that this equation simplifies quite a bit for simple situations. For instance, the electron in the ground state, this whole ugly thing just simplifies to this, where r0 is the Bohr radius, and then r is the distance from the nucleus. So you actually get a fairly workable equation here until you get to more complex things going on. All right, let's finish off with an example, and the calculations for the particle in a box or infinite potential well problems aren't all that tricky. They're very similar to what we saw with the Bohr model, where we're just looking at energy levels and sometimes looking at wave functions. So if I want to find the 3 lowest energy levels, I'm assuming I've got an electron trapped in my box, and it's a very small box, 10 to the negative 10th, so about the diameter of a hydrogen atom. So our general expression using this model of a particle trapped in a well is n squared h squared over 8ml squared. So I'm going to go ahead and find the first energy level, where n squared is just 1 squared, so it's 1. I've got Planck's constant squared, so 6.626 times 10 to the negative 34th. Got to square that guy. Over here I've got 8. M is the mass of the particle that's in the box, so this is an electron, 9.11 times 10 to the negative 31st kilograms, times the length of the box, the width of the box, so 1 times 10 to the negative 10th, and we have to square that. This gives us 6.02 times 10 to the negative 18th joules, which, by the way, converts to about 37.7, that's not a 7, electron volts. So this is not accurate at all, because it should be, for a hydrogen atom, it should be 13.6, right? So again, not a good model for an atom, but just an example of how we can apply quantum mechanics. So the rest of them, E2, is just going to be n squared times E1. So it's just going to be 4 times E1. I won't bother writing that all out again, which gives us 2.41 times 10 to the negative 17th joules. And then if we want E3, it's going to be 3 squared, so 9 times E1, which gives us 5.42 times 10 to the negative 17th. Okay, and then we can also play the same game by saying that the particle can give off a photon in the transitions. So if we go from the n equals 2 state to the n equals 1 state, and we want to know the wavelength of the photon that is emitted, we basically do the same thing we did with the Bohr model. So we've got hc over energy, or the change in energy in this case from one level to the other. So that's hc over E2 minus E1. And we could go ahead and plug in the E2 and E1 because we already found them. Or we could say, well, E2 was just 4 times E1, so I'm going to have 4 times E1 minus E1. So this will just be hc times 3 over 3 times E1, which gives us 1.1 times 10 to the negative 8th meters. Alright, there you go. Particle in a box. See you next time.